Then I would directly invite our next speaker, Konstantin Schauerbecker, Dr. Konstantin Schauerbecker. The stage is yours.
Much.
This is your pointer.
Where's the presentation? So?
I think it should load. The team behind will load the presentation, and then you can go ahead.
Mm-hmm. Okay, so good morning, everyone. My name is Konstantin Schauerbecker from Nerian, and I have the pleasure today to talk to you about stereo vision. So, first of all, though, I want to say a few words about Nerian, who we are, what we do. Nerian was founded back in 2015, right here in Stuttgart, where we are still located. And basically what we do is we make high-speed FPGA-based stereo vision cameras. And yes, this is our key technology on which we've been focusing ever since. And we supplied our cameras all over the globe to numerous prestigious customers. And as of this year, we are now a member of the TKH Vision family. So this time you can actually find us at the TKH Vision booth in Hall 10. So first, just as a recap of how stereo vision works. Stereo vision is a passive sensing technology. So in essence, this means we don't have to emit light for performing our measurements. We can just use the ambient light that's there on the scene anyway. Basically, it's mimicking how we humans are able to perceive depth. So we are taking two images from different viewing positions, and we can infer the depth information just by correlating these two images and finding corresponding points. That means that actually all of the intelligence is in the image processing. And if you want to do this well, you need to throw a lot of computing hardware at it. And this is the key challenge here, the high processing demands that stereo vision implies. So how does it compare to the more conventional active 3D sensors, such as time-of-flight or structured light cameras? Yes, as I said, the key difference is that, well, we are passive, we don't have to emit light. And that has some key advantages. So I think for us, number one advantage is that you can take a stereo camera outdoors into the bright daylight, and it will work just as well as indoors, because we don't have a contrast problem. We don't need a projector that can be overcast by the sunlight. In the same sense, we're not really limited in range as to how far we can sense, so we can do long-range sensing with a stereo camera. You just need the right camera setup. We can have multiple sensors with overlapping field of view, and we also can do a color perception with a stereo camera. But there's one major downside to stereo vision, and that is that we need visible texture information. So a textureless surface, like a blank white wall, cannot be measured because there will not be any visual information there that we could sense. To overcome this problem, what can be done is a hybrid approach, where we have a active pattern projection together with a stereo camera. So there's an example scene here, which is actually very challenging for a stereo camera, because there's no textures in the background. The foreground objects have very little texture to them. So this makes sensing particularly difficult. And if we look at the depth map that we get from here at the bottom, so the purple colors means a closer depth to the camera, we can see that we have quite some large gaps in the measurements. And we can now, even in such a difficult scene, we can get near perfect measurements if we have a texture projector. So we have here on the top right corner, we have the scene, what it looks like with the projected texture on it. And then we get this very dense depth map that we have at the bottom. But now with Now with this so-called active stereo vision approach, there's one downside again, and that is that, well, now we can't do any color perception anymore because, well, we have this pattern that's going to interfere with our sensing. And so this was our motivation for the design of our latest stereo camera that we have been releasing here at the Vision show this week. Which is here our new Ruby 3D depth camera. And now Ruby integrates several things into one camera. We have two monochrome sensors, so these are the outer ones, which we use for stereo vision depth perception. Then we have a random dot laser projector in the middle, plus a third color sensor that is used for the color sensing, all integrated into one single camera unit. The way that this camera works is the random dot laser projector uses infrared light that is visible to the monochrome cameras that we use for depth sensing, but it is not visible to the color cameras. So we can do color sensing here without getting artifacts or altered measurements from the pattern projector. The pattern projector itself assists depth sensing for indoor and close to mid-range applications. But for outdoor applications, when there's larger measurement distances or brighter ambient light, we can still do entirely passive 3D sensing without the projector. And yes, and because we have a split between these monochrome and color sensors, or because we have the separate color sensor for the sensing, we can use these superior monochrome sensors for stereo vision, which is very beneficial because we don't have any color matrix in front of the sensor that introduces artifacts or reduces the light sensitivity. Now, if we look at some example pictures that we recorded with our new Ruby camera, this one here is an example for a challenging indoor recording. So we have this palette here that's been loaded with bags, and actually the entire palette is all foil wrapped, which makes this a difficult surface to measure. There's also not too much texture there to be seen, but still we get this very dense depth map that we can see on the right, where we can even make out the boundaries between the individual bags, as well as we even see in this completely blank white background, we still get pretty good dense measurements. If we take the camera outdoors, this is the performance that we get there. So here definitely is just as good or even better than for the indoor case. So we get a very dense measurement here. Even though this was recorded at a bright day where the projected pattern was not visible, but we have a lot of texture here in the image. So we don't need a pattern projector here if we have enough texture here, that can be seen. And in our experience is as soon as you step outdoors away from a clean indoor environment, suddenly you have texture information everywhere, and then you don't need any active projection anyway. Then there's one more thing that our Ruby camera does, which is it aligns the color image to the depth measurement. So in fact, there is physically a small parallax between the color sensor and the monochrome sensor, but because we have the 3D measurements, we know where everything is located in space, we can do this alignment, and suddenly we have for every single pixel, we get exact color information and depth information. So we can actually generate a colored 3D point cloud in real time from the measurements. And by the way, this is something that you can see today at the demo at our booth, where we showcase a real-time live colored 3D point cloud display. Some other specs about the camera. So what performance can we achieve? We can achieve image resolutions of up to 1.5 megapixels with the cameras. We can achieve up to 60 frames per second. though not at the full resolution, but you have a choice there between whether you want to prioritize image resolution or prioritize frame rate. In general, what our constant is that we can achieve 24 million 3D points per second, and it's up to you to divide that up between frame rate and resolution. Also, the camera integrates a built-in inertial measurement unit, which I find is a very important feature for all mobile robotics applications. And despite of all these features that we integrated, it's the most affordable camera yet that we have brought out on the market. So it's, in my opinion, a very cost-effective sensing solution. A brief look what's inside the camera. Yes, the key here is the FPGA that we have built in. So we have a powerful FPGA inside that camera, and on this we run all the image processing with our proprietary StereoVision pipeline. And this means because we're doing all of the processing inside the camera, that no computations have to be done on the host PC other than the application-specific application that the customer wants to run. So it's all of the computing resources of your PC, they are there for your application. You don't have to do any 3D image processing, low-level 3D image processing yourself. Then also because of the FPGA, we can achieve a very low latency for the measurements. Then the device also has a low power consumption of just 9 watts, which allows this to be easily integrated onto mobile battery-powered systems. And it comes with this very small and compact form factor. On the software side, we can program Ruby with all of the software frameworks and libraries that we support with our other cameras. This means that we have an open source Python and C++ API. We support the popular open source frameworks like ROS, but also OpenCV and the Open3D library. But we also support all of the well-known machine vision software suites like Halcon, Matrox, Neurochex, and others, as we are also fully GennyCam compatible. So with that, I'm at the end of my presentation. I would invite everyone to just to come and have a look at our Ruby camera for yourself, or at our live demo. And you can find us just at the TKH Vision stand in Hall 10, which is not very hard to miss. So thank you very much for your thank you very much for attendance.
Please give a big round of applause to all of our speakers. If you have questions for Martin, then please go ahead. Yes.
I enjoyed your talk. Thank you so much. I had a couple of questions. First one was that you talked about the color camera. Does it require its own light, or is it okay working with the ambient light in the environment? Ambient light, is it enough for that color camera?
Yes. Okay. It depends. It depends.
Okay.
If it's completely dark, of course, the color camera won't give you color information. The depth camera will still work because it can see the laser illumination. But if it's too dark, you might want to use some additional light if there.
Okay. And how about reflective surfaces? The depth camera is independent of the reflectiveness of the surface, or? Yes,
reflective surfaces, they are always a challenge. If the part is not very highly reflective, it can work okay. If you have a very shiny part, what can happen there is that you get a depth measurement of the scene that's mirrored in the part. So suddenly you get a whole
void area.
Yes, a void in that part. But typically, from an analysis perspective, such errors are easy to detect and to filter, because you just need to threshold, for example, your depth, and anything that's farther away than a given distance is likely a reflection if you know what distance the parts have to the camera.
And is random noise enough as a pattern for depth measurement, or
yes. The thing is that we don't. The camera doesn't just look at the pattern, but it also looks at the surface of the parts. So it's more of a support for the depth measurement, the pattern projection, and if we have a surface that has no visible texture at all, then the laser pattern, it provides anchor points for the measurements, and then we have a large interpolation between the patterns. But if we have just a little bit surface texture there, then we can use both information for the measurements.
Got it. Thank you so much.
Welcome.
Any more questions? If not, then I have another one. So you mentioned low latency. Do you have some numbers?
So what?
You mentioned low latency.
Yes.
Do you have some numbers for us?
Yeah. So it's about the time between 2 frames.
Yes.
So if we run the camera at 60 frames per second, then we're at 1/60th second latency.
Ah, okay.
Yeah.
And the product is also FPGA based, and we heard from the previous speaker that was also FPGA based, right? The C6 imager. So how are you competing, if you are competing at all?
I think we are at very different applications. So we have our typical applications are real-time applications where we have to systems that interact quickly with a dynamic environment, and where we need to capture a full frame image, and not so much at the production lines for us.
And when you say real time, the real time requirements are coming from the customer, right? So
yes.
Real time is something very difficult to put onto paper. We claim real time, but what real time is for each application,
yes.
It differs.
Yes, it depends. It depends.
But thank you very much. It was a lovely presentation from all 3 of you. I would invite you all to contact them if you have any more questions. They have all booths here. You could find the booth information on the slides as well. I thank you all for your attention, and I thank you all for your interesting presentations.